ITP. Está bien, está bien. Yo he mirado alguna charla en ITP. Después de estar allí, sí, sí. Una vez que no pude ir y después vi el database y había una muy famosa de Adiós Fire. Sí, sí, sí. Presentó el Toric Code, estaban parties y todo, fue la primera.
Good afternoon, everyone. Welcome to our colloquium of today. And it is my pleasure to introduce our speaker of today, which is Professor Susana Huelga. She got her PhD in theoretical physics in the University of Cantabria. Her supervisor was an old friend of some of us, it was Professor Santos. And Manuel wants me to say that you studied in Salamanca.
Yeah.
After her PhD, she was a postdoc at Clarendon Laboratory in the University of Oxford, at Imperial College, also in the UK. Then she stayed around in the UK, and now she's a professor in theoretical quantum optics at the Institute for Theoretical Physics in the University of Ulm in Germany, and also a collaborator of the new Center of Quantum BioScience, again at the University of Ulm. In her own words, the common denominator of her research is the exploration and exploitation of quantum coherence and quantum correlations for information processing. Information processing is an important keyword at this institute. And she has contributed in a number of aspects in this general topic, including quantum information processing in noisy environments, where, for instance, she was one of the first to show the phenomenon of stochastic resonance also in coupled quantum systems. She has also worked on quantum metrology, coherence effects in complex systems, with significant contributions in the study of noise-assisted effects in biological systems. I think this is what she will be talking about today in general, and also in this aspect of quantum biology. Let me mention that she's one of the authors of a white paper of the European Science Foundation on research on quantum biology. It's a pleasure to have you here, Susana.
Okay, thanks, Maxime. Okay, so many thanks for the invitation to Maxi and Roberta. It's always a pleasure to come to the Institute, to come to Mallorca. So maybe, can we make it a little bit darker? Is it possible? I think, okay, that would look nicer. Right, so you will have to wait a couple of slides to see what is the reason for this very festive motive, yeah? But you see that there is a rationale behind it. So there are three contexts in biology where there is the suspicion or there is indication that there could be some relevant quantum effects. I call them non-trivial in a sense that I will discuss in detail a little bit later on. So one is related to magnetoreception and bird navigation. The second one is related to olfaction, where some people argue that perhaps a vibration-assisted tunneling process is responsible for this. And the third one concerns the primary steps in photosynthesis, which is what is going to be the bulk of this talk. While, let's say, the experimental data supporting the first two topics, magnetoreception and olfaction, is very modest. Here you will see that there is a very strong body of spectroscopy, both linear and non-linear, that somehow acts as a benchmark for the type of modeling you can do. And let's say that you have to be consistent with many data. So it's a sort of security network that we don't get too wild in speculating. Okay, so this is the outlook of the talk. I will discuss first. So I will try to make it as self-contained as possible. So it will be more of a conceptual talk than a technical one. But as I'll be here until Friday, so should you be interested more in some technical aspects, we can also discuss it afterwards. So my aim is to provide you a sort of state of the art of where things are at the moment, so that you get an idea of the field. And for that, we need to present what sort of systems are we actually talking about, and what type of experiments have been performed to probe them, in such a way that experiments have led to people arguing that this type of system, pigment protein complexes, which we introduce in the slides, exhibit or can support long-lived coherence. Maybe this is a wording that you've heard in relation with this topic, and that we need to scrutinize and to clearly explain what we exactly mean with that. Then we'll put forward what we believe is a sound theoretical framework to account for this type of observations. That's going to be a bibronic model of molecular aggregates, where there will be significant mixing between electronic and vibrational occlusive freedom. So my aim is to convince you that within that framework we have reasonable agreement with the experiments. We have sound microscopic models from the viewpoint of an open quantum systems approach, and moreover, we can formulate tasks where we can argue that the performance of the system will be enhanced by the presence of coherent phenomena. Okay, so this may bring you back to biology 2 in your high school. And I guess that probably we've all at some stage got a little bit fascinated by the type of machinery that nature has developed in order to transform sunlight, well, in some form of fuel, depending on the type of complex you were talking about. So this is a very complicated process where many things happen in very different time scales and space scale. We're going to be concerned with what people in chemical physics call the primary steps in photosynthesis. So those are the processes that will happen in a time scale of a few picoseconds, where light is going to be collected by some specialized molecules, and then a range of molecular wires will be able to transfer an electronic excitation to a selected region where actually charge separation will happen, a transmembrane potential will be established, and that will be the beginning of all the photochemistry that will end up producing ATP. So for instance, in the case of higher plants, these are molecules that are hosted in the thylakoid membrane that sits in these specialized organelles called chloroplasts. Okay, so now you see the relation with our cover page, because this is a cartoon, well, more of a sort of simulation, and this is actually AFM images of the photosynthetic apparatus of purple bacteria. So you see that this one has a particularly nice geometry where we have peripheral complexes that will be in charge of transferring the electronic excitation triggered by absorption of sunlight to some units where finally in the reaction center the transmembrane potential will be established. Depending on the type of organisms, then there is a variety of geometries and even different type of highly absorbing molecules involved, while the architecture of the reaction center is relatively conserved across species. This is still, as you can imagine, and if we see what would be the type of crystal structure that we have, this is going to be a system too complex for trying to do the type of first principle calculations we want to do, that will fall into what can be done state of the art at the level of even being able to provide numerically exact solutions. So for most of the talk, I will actually use as a test bed a particularly simple type of molecular aggregate, probably a curiosity from the biological point of view, given that it's only present in a type of very sad bacteria that live in some highly deprived areas where every photon is precious. But it has the advantage that it's only made up of 7, this one is considerably less coupled to the rest, so most of the simulations will involve 7 bacteriochlorophylls. So for us, chromophores, if you want. These are going to be molecules that will be in charge of absorbing light, and by means of their interaction, it will be possible that I can move from the area where absorption happens to the final destination across this network of coupled chromophores. The estimation of how long it will take from absorption to the reaction center lies in between, let's say, 0.5 to 5 picoseconds. So this is the type of time scales we're going to be interested. Once absorptions happen, the probability that an absorbed photon will yield to a charge-separated state is of the order of 95%. So that's why this protein was actually the first one to be X-ray crystallized. It's called the phenamathine, also the FMO complex. This is, I call it the James Cummings of quantum biology, in the sense that is very, very well studied, both at the level of structure. This is in fact the type of information you would get from the protein database, and also there is an enormous amount of results coming from spectroscopy. So should you produce a theoretical model trying to explain what has been measured, then there are many tests you have to pass so that you can reproduce all the spectroscopy and claim that your model can actually be having something to do with reality. So this is the type of aggregate that we will be considered as a model system, and that allows us to illustrate what is going to be the typical structure of a pigment protein complex. So what we have is a network of, well, in this case, they are bacteriochlorophylls, we really don't care, that are embedded in a protein cage, in a protein scaffolding that will be the elements that allows for, well, actually the structure being held in space, and also any possible arrangement of the orientation of the bacteriochlorophylls. So the local environment of each chromophore is slightly different, so then the energy that it will have will range from 1 to 8 in our case, values that can extract from linear spectroscopy, and should the interaction in between chromophores given that the proximity is going to be sufficiently small, can be in the range of 10 to 20 angstroms, then I can formulate a way to couple them following excitation, right, as just a dipolar couple that will depend on how far they are in such a way that should illumination happening here, now I have the possibility to let this exciton migrate across and finally reach a reaction center. Take into account that if the chromophores are sufficiently close, then this Hamiltonian will yield to the formation of more or less delocalized excitons. And given that pigments will also be coupled to the protein surroundings, then depending on what is the ratio in between the electronic coupling and the electron-phonon coupling, then the effect of this phononic bath due to both the protein and possibly intermolecular modes. This can yield from simple frequency shift to maybe the formation of hybrid states in between electrons and photons. Okay, so what is the experimental background in arguing that, in fact, and contrary to the cartoon I was using initially, in fact, the process of excitation transfer across FMO, for instance, will not happen in this sequential manner, but actually, when the system is probed in such a way that I can be sensitive to excitonic delocalization, I actually conclude, and these are very pioneering work by the group of Graham Fleming, led by senior postdoc at that time, was Tobias Brixner. They argue that we monitor this process as a function of time and frequency and show that excitation energy does not simply cascade stepwise down the energy ladder. So, does this indicate that we may be talking about some form of coherent dynamics in this type of processes? I think to explain in detail how two-dimensional electron spectroscopy is performed is rather convoluted, but the main idea, I think, can be understood if you think about a very simple situation that we know very well from quantum optics. That is, considering the type of signal we have in a Ramsey interferometer. So imagine that you have a very simple situation where the aggregate is actually only made up of two chromophores, okay? So these chromophores, if I use now the bases that diagonalize the electronic coupling, I will end up, well, I will have some ground state, two excitons, and a double excited state in there. So imagine that I tune the interferometer in such a way that is resonant with this excitonic splitting. I should then be able to prepare, by means of a pi/2 pulse, an equally weighted superposition of two excitonic states. If I now have a time of free evolution between this preparation and a subsequent measurement, I can accumulate a definite phase relationship between these two states. Okay? If I now probe the coherence that has built up during the free evolution by means of another pi/2 pulse, and I check for the population of the two different excitonic states, well, typically I will have a sinusoidal signal. Okay? So, if I perform the experiment in absolutely ideal conditions, then I will have a signal that is able to exhibit full population inversion between 0 and 1. Should I be exposed to some environmental noise, we know that the type of Ramsey signal that I will obtain, it will have a sort of exponential envelope. Okay, so the important thing is that by probing this type of systems, with experiments where you are able to both generate and detect coherence, then you realize that there is a very different magnitude for the value of the lifetime of what would be superpositions involving the ground and an excitonic state, and the lifetime of superpositions that involve excitonic states. Okay? So while this one is of the order of 50 to 60 femtoseconds, to something very, very fast, loss of coherence, what they encountered in the measurements was that the lifetime of excitonic superpositions, the time scale over which I have a sinusoidal signal that I claim to be associated to the excitonic dynamics, is much more long-lived. So the wording long-lived coherence, long is long with respect the typical optical dephasing time I would have between ground and excited. Given that the time scale where these excitonic superpositions will last is comparable to the total transfer time, then this opens the expectation that given that I have a coherent dynamics in the time scale where things relevant happen, maybe there is a way to argue that this presence of coherence is not just a byproduct of being analyzing a femtosecond time scale, so a picosecond time scale, but may actually have a more relevant role. Not go, it will take a couple of hours to discuss in detail how to evaluate the third order response you have in the type of experiments that have been implemented. But just in case there is some experimentalists in the audience, those are more complex than the simple Ramsey setup I explained, and would imply the illumination of your sample with 3 femtosecond lasers with well-defined time scale, so time separations in between. But from the theoretical point of view, what you would have to evaluate would be just the third order polarization. And there is a well-prescribed way to do it. You could even been able to compute it numerically exact, even for fMRI. Okay, so the initial experiments by Brixner were later on supplemented. Probably this is the paper that made higher waves by still the same group, but now with Greg Engel, a senior postdoc in 2007, and then Greg later in his own lab also performed experiments going from, I think the ones from Brixner were at 77. He also had data claiming to still detect persistent oscillations at room T. Okay, so I think in sort of neutral terms, you could say we have experimental observations that point towards having a coherent dynamics when probing this type of molecular aggregates involved in the primary steps of photosynthesis. So this opens the prospect of a possible relation in between coherence and biological functionality. Or maybe more stepwise, and especially from the point of view of somebody interested in the kinds of open systems, you can say, well, the first thing I would like to see is to understand how it's possible that even at room temperature and in an environment that, as I will show in a moment, is characterized by a spectrum of the fluctuations that is definitely far from white noise, how is it possible that there are still coherent remnants in those time scales? And then beyond, so let's say even if you would do that and convince yourself that you have a microscopic way to understand it, then let's say the connection with something that biologists would be interested on would be saying, okay, now we know that it's there, I can benchmark it and model it. Now, is it useful for something? And take into account that ideally you would go beyond establishing correlations that certain magnitude grows at the same time that the coherence is enhanced. But you would like to identify some task that actually you can prove that either it could not be performed in the absence of a coherent interaction, or the efficiency is definitely enhanced. Yeah? So let's say a very dramatic illustration would be in quantum information. If you think about the process of performing state teleportation, you do need to share a bit of entanglement to have a fidelity 100%. If you don't have it, you cannot do it. Okay? So we would like, ideally, to be able to find something like that happening in a biological context. This is very challenging, I would say, and still pending, but I think we have some news from the initial part, at least to understand what may be happening in there. Okay, so I mentioned before that we had sufficient information from the spectroscopy camp to be able to build up a Hamiltonian to describe the process of energy transfer across FMR. So I can have information about what would be, well, this was to see that there will be some error bars corresponding to different analysis, but given that I also have information about distance, orientations of the dipole moments to build up the strength of the coupling, in principle, I could put numerical values in here and see what sort of dynamics I would predict. Moreover, we know that this electronic network is embedded in a sea of phonons of all sorts that I need to describe as well. And the first attempt you would do is saying, okay, definitely there will be a rather complicated interaction in between the chromophores at the different elements of the protein surrounding, but what I know is that the faster time scale where nasty things happen is going to be due to pure dephasing in your local sites. You may have losses as well, but this will happen definitely in a picosecond sort of range. So the probability that you will lose the excitation during the transfer is very, very small, but dephasing will be messing things around. So the type of behavior you would obtain if you calculate what would be the probability that a given excitation will reach the reaction center as a function of time has this typical behavior. If you would consider a purely Hamiltonian evolution, then probably unexpected you encounter that the system is very inefficient for transferring excitations, because you have the risk that there may be delocalized excitons that don't have any overlap with the one that is closer to the reaction center, and then you leave part of the energy in a limbo. Okay, so in fact, you would have that in the absence of any phonon bath, the probability to reach the reaction center is only 50%. In the moment that you set noise in the moment that you increase the value of the dephasing, then you see that you start increasing actually the value of the probability to reach the reaction center more and more, and you see that, okay, the combination of the coherent electronic interaction in the presence of this phonon path seems to at least work, in the sense that, well, even classically, I can think of dephasing just providing a way to activate transfers that were just energetically not favorable, or beyond even being able to remove or to activate paths that were forbidden when you only had a coherent interaction. So this is the typical behavior. If you would represent what is the probability of transfer as a function of the noise strength. You have a sort of broad resonance telling you that there will be a range of values of the dephasing for which you will manage to have a 100% success for your transfer in the required time scale. If you carry on increasing the electron-phonon coupling, in other words, in your model, increasing the dephasing rate, then you really would inhibit the coherent coupling and then reduce again the probability of success. So then, with a very naive model, you can think that actually the transfer in this type of molecular aggregates could be thought of as a noise-assisted process. As quantum opticians, you can imagine nobody would have a doubt that indeed that would be a way to think of it. There have been different implementations using different technologies. Probably the nicest experiment, also because it was the latest, was this demonstration, right? Where you see how they reproduce the type of curve we have for the transfer as a function of the efficiency in a chain with 10, in a qubit network with 10 elements in the group of Heiner Vladimirsburg. Okay, but I told you that we have a lot of information concerning the spectroscopic probing of these complexes. So if you go with your model that includes electron-phonon interaction at the level of just pure dephasing model by a Lindbladian master equation, you will realize that you don't go very far. So definitely you can produce a sort of qualitative understanding that it's very likely that we will have at play a combination of coherent interaction ruled by a Hamiltonian and dissipative processes. But we need to sophisticate the model in order to account not only qualitatively for saying I transfer 100% probability in 3 picoseconds, we also need to account for all the fingerprints that this system leaves when probed differently. If you have a look at the type of spectral densities that would characterize the fluctuations of the phonon path, you will encounter, depending on the complex, so everything we say, we know in open systems that nothing is black and white, whereas in addition, a large molecular aggregates is even less so, right? But generally, we will encounter that the spectral density is very, very structured. So in the vicinity of excitonic transitions, we will have some modes. We will also have high energy components, and we will also have a little bit of action in the limit of omega tending to 0. So we know that a lot of non-trivial things will happen if I move from the Lindblad realm to the cases where the electron-phonon coupling is considerably more involved. Moreover, the strength of the coupling between chromophores, so the electronic coupling, and the electron-phonon coupling in many situations are comparable. So let's say the type of arguments I will put forward to try to redefine a system governed by a Hamiltonian subject to some form of residual path always have to be considerably tested to be sure that the master equation that we are putting forward is meaningful. It's very difficult to think about doing a completely ab initio derivation. Okay? There are many unknowns even concerning the nature of the coupling. So here the procedure would be more formulate phenomenologically master equations, try to benchmark them with numerically exact procedures, face them with experiments and readjust. So it's a little bit of a feedback strategy. Okay, so this is what I will present. I will put forward a microscopic model that I argue will have not only the required transport properties, but also will be able to account for the two-dimensional response. Try to be predictive. So some experiments done with artificial aggregates seem to be nicely described by this vibronic model. And moreover, we will show how here it comes naturally a task. I can identify a task that is clearly coherence assisted. So setting some ground for arguing that maybe the role of coherent interactions goes beyond what would be the trivial formation of chemical bonds, let's say. Okay. So maybe anticipating results is going to be crucial for our model that exciton-phonon mixing will happen. In the first case, I will focus in the mixing that will happen with modes that are quasi-resonant with excitonic transitions, and then we will see that the model survives when I really consider spectral densities that include a lot of structure in different ranges. Okay, so that's one of the few slides that is a bit more densely populated. So again, fitting a bit the jargon, I use R's and J's, so Latins alone, to design the side energy. So this will be optical transitions. Think of a dimeric system concerned with just two chlorophyll molecules. They sit in different parts of the aggregate, so then the side energy may be different. As a result of the electronic coupling, I can think of making a description now in terms not of side states, but possibly the localized excitons. In some complexes, like the round ones I show you, this is a case where excitonic delocalization really involves the whole aggregate, right? In the case of FMO, these excitons are only delocalized across 2 to 3 pigments, not the whole complex. Okay, so the key observation comes if you think about rewriting the total Hamiltonian, right, in such a way that we have the side energies. I modeled the path of phonons in terms of harmonic modes. Sides will couple electronically via a dipolar interaction. And in addition, and this is information that comes mainly from molecular dynamics, it seems that the main source of dephasing comes from the local pigment environment. So there are certainly shared modes due to the protein scaffold, but their effect will probably be only felt on a larger time scales. So I think it's well grounded to model initially the dephasing as really coming from having each side coupled to its own path of phonons. described by a spectral density that will contain in particular some modes whose frequency is very close to that splitting. So if I will write what is the effect of these phonon modes in the excitonic basis, then you see immediately that the interaction Hamiltonian with the phonons includes terms that can couple the two excitonic states. Right? So in a cartoon form, even if the local dephasing is able to dephase ground-excited superpositions in a very short time scale, if my experiment is such that it produces superpositions between excitons, then what happens is that in these bases, right, I may have some residual background that will try to bring me down to the lowest energy exciton, but at the same time, I have a quasi-resonant mode that will be repopulating, if you want, that superposition. So I have built in a mechanism that would allow both spontaneously generate coherence, but also being able to regenerate the one that is lost to the broad background. So this is just very phenomenologically telling you how in the presence of a structured density, spectral density, I can think that the behavior of superpositions, ground-excited and excitonic ones, may actually be different. If I look in the literature to see what is the strength of the coupling electron-phonon, then this is context normally quantified in terms of the so-called quantitative factor. Anyway, the strength of the coupling, you see that there are large variations from one complex to another. Okay? So what we are discussing will not be completely generally valid, or beta will manifest more strongly in one complex or another, okay? Depending on the ratio in between the electron-electron and the electron-phonon coupling. Given the level of uncertainty that we have both on the spectrum of the fluctuations and even in the ab initio that we are starting with, what would be ideal is to be able to show that we are saying makes sense without the formulation of any master equation. So we try to put forward a numerically exact method to indeed see whether these excitonic superpositions are long-lived in the high T domain. So this is something that we did initially at the level of a dimeric structure that models the lowest energy manifold of FMO, which is probably the responsible of most of the spectroscopic features in 2D. And the idea is that a configuration like this, where we have each pigment subject to its own bath of harmonic oscillators, can be transformed just unitarily into a configuration where the effect of the bath is now represented by these semi-infinite harmonic chains, where the coupling goes only to nearest neighbors. So this is a configuration that is friendly to be simulated with the MRG. So what we show in a moment is what would be the behavior of our excitonic superpositions when I have a spectral density that includes a broad background and some sharp spectral peaks resonant with the excitonic transition. These are data at 77, so then you can see that in the absence of the sharp mode, my oscillations will essentially disappear by this time scale, where I can definitely enhance them if the mode is present. The other ground-excited superpositions are essentially immune to this spectral feature. And the nice thing is that if we carry on doing the calculation, the simulations in the high T domain, we still see signatures of excitonic coherence, even at room temperature, entering into the picosecond regime. So let's say this type of model points towards the possibility that indeed there could be even purely electronic coherence in these time scales at these temperatures. Now, take into account that the evaluation of the third order polarization does not allow you directly to access the dynamics. In fact, the relation between the two is non-trivial. So there is a lot of information coded in the nonlinear response, but unfortunately it's all convoluted with many other things. So I would say that the presence of oscillations, the presence of coherent behavior at the level of the dynamics, take into account that this is computed from simulating the dynamics of the whole thing, right? So really I propagate here the whole universe, and at every time I'm interested on, I trace out all the modes, and I have what would be the electronic state. And what I'm plotting there would be the value of the real part of the off-diagonal elements. But this is not what you are measuring directly in 2D, okay? Should you have the possibility to do a Gedanken experiment where you really extract, tomography the state, then we could compare the predictions directly. But what we have to do now is also argue that the spectral response of this microscopic model also has something to do with what has been observed. Yeah? Of course, theoretically, you have the possibility to evaluate separately the weight of all the different Liouvillean paths adding to the final third order polarization. And let's say that the model is indeed consistent with having coherence both at the level of excitons and directly measure at the level more of, sorry, this is only the vibrational. We will have excitonic components, and I didn't put here what would be vibronic ones. Anyway, this is only to indicate that the microscopic model would have a type of spectral response that at least is not disparate as compared with what has been mentioned. There is also a possibility to do some experiments to try to check whether indeed we can reproduce the observations, and well, with artificial systems one can use particularly suitable configurations where this picture of having the excitonic transitions close to some sharp modes fits very nicely. Perhaps even more relevant, and at the level of natural ones, if you remember I told you that the architecture of the reaction center is relatively well conserved across species. So therefore, it's quite likely that something really crucial, really optimized, may be happening more at the level of charge separation than at the level of excitation transfer. So experiments of the same type, and also by groups that have nothing to do with each other. Some people are suspicious that all the other data come from Fleming's group, right? But these ones are competitors. What they showed was a correlation, right, in between the efficiency of charge separation and the position of selected modes. So for them, this is a proof, let's say, of the relation between coherence and function, but I think we will all agree that, well, it's a nice sort of correlation. Okay, so if you look in the literature, and these are the two latest experiments I know concerning FMO, I would say that the vibronic model is not in disagreement. So the interpretation of the data would sit reasonably well in there, but not everybody agrees. So Dwayne Miller, which is a person very well known in control, he has tried to essentially design an experimental setup very similar to the one Engel was utilizing in the 2007 paper, and he claims that all the oscillations that he observes really are vibrational in origin. So in the most boring case, it could even come only from the ground state and just having the same, the 0-1 phonon oscillations. I would think it's rather unlikely, right? But it will be better to have a second generation of experiments where these type of ambiguities are definitely completely cleared. I've even suggested that there should be a provider of FMO just handing samples to different labs. They will do the experiment, come together and see whether, at least conclusively, and as far as 2D response is concerned, we are 100% certain. So if you want, said differently, nobody doubts that there are oscillations in the response, so that there is coherent dynamics. What is debated is what is the origin of those, or the nature of those oscillations. Are they purely vibrational? Are they purely electronic, as Engel initially argued? Or are they vibronic, as we argued, and I think on reconsideration, Engel and Scholz would also agree. This is actually a theory work, right? We're considering the type of aggregate that is present in the photosynthetic apparatus of a type of algae, also a very well-studied complex. What they concluded is that fine, excitons definitely form, and you can argue that you can already conclude that from linear spectroscopy, but what we don't detect in the simulations are excitonic beatings. So in other words, the relaxation of the system will just be a cascade, thermally funneling the higher to the lower exciton. Okay? Greg Scholz, an experimentalist, was also part of this theory work, where they did actually a very, very complete analysis, right? They even calculated the spectral density from molecular dynamics. But I will show you in a moment that there could be some problems. And in fact, probably a bit dissatisfied with this incoherent relaxation of excitons, he came down and repeated experiments in his lab, concluding that, highlighting the importance of further investigation of the interplay between coherent coupling and nuclear degrees of freedom. So still opening the possibility that actually what he measures indicates that there is electron-phonon mixing, that the relaxation of excitons is not a merely incoherent process. Okay, so this is actually unpublished work. This is the first time these simulations go into the open, so taking it with care. But this is work that we are doing at this very moment, where we are trying to simulate two model systems. One, probably not very interesting biological. This is a protein present in cauliflower, but very well studied due to the simplicity. It's a nice dimeric compound, very well characterized, so we can then benchmark many figures of merit. And the other one is the one we suspect that is really probably the most interesting aspect, or the more interesting scenario where coherent effects may be relevant, which is the special pair in the bacterial reaction center. So what we try to do, what we have, the results I'm going to show you, are exact simulations using two different methods. One is the one I showed you before, when we try the MG type of propagation, And the second one is using this called hierarchical equations of motion. So these are two numerically exact methods with the pros and cons and their better performance in one regime or another. And what we are doing is simulating everything. So they are not embeddings as they were done in the theoretical work I've just commented upon. So really we want to have the full effect of this discrete part of the spectrum at higher energies and see whether the microscopic resonant model survives. Laboriously reproduce the absorption spectra as the initial check that indeed the model is able to support a comparison with experiments. This is the first thing you will have to do. And then the second is the re-evaluation of excitonic coherence in the presence of this now complete spectral density. There are several interesting things coming, so that the role of the high energy modes is highly non-trivial. There is a very strong renormalization of the electronic parameters. But if we focus only on the behavior of the coherences, we do find that both for WSCP and for the reaction special player in the reaction center, the presence of modes such that there is a significant mixing between electrons and phonons does sustain the oscillatory period. Okay? So the condition of resonance may be sufficient and will be the one that yield to a, let's say, more flashy persistence, right? But also in situations where you have no clear modes. This is the position of the splittings in the two type of complexes. Even if you are in a situation surrounded by many or sufficiently far away, we do have that the biclonic model exhibits long-lived coherence. We are trying to compute the spectral response as well, with the help of let's say with a phenomenological model, including few modes, not the 55 that the real spectral density has for WSPC, but even there is the possibility that we can compute the spectral response exactly. So then to be sure that indeed at the level of the dynamics, this type of interactions do exhibit long-lived coherence. Is that useful for something? You say, well, this is simply, instead of talking about chromophores, you can talk about any other thing, right? And just have your figure of merit, the spectral density, and argue, well, what sort of behavior you would expect. So to convince the biologists that something interesting may be happening, here comes the issue of arguing whether this mixing has any effect. And for that, one way to look at the problem that I think is particularly nice for deriving quantitative relations is think about the thermodynamical performance. Because one can think of our network of chromophores as operating in between a hot bath provided by the sun radiation and a cold bath provided by the phononic reservoir. So in these last couple of minutes of the talk, I will show you that depending on whether you have here a network of chromophores that couple coherently by a dipole-dipole, or I have a network where for each chromophore I have some vibrational modes. In this case, they were quasi-resonant. The thermodynamical performance of these two machines, where in one of them excitons relax thermically, versus another one where detail balance will be broken, yeah? So the electron-phonon interaction is present, and should I look at the electronic submatrix, then I will see that I have terms that cross, can make the excitonic levels to talk to each other. So I think I only have time to just indicate how the calculation will be done. If I consider a model where I have some coupling electron phonon that is coherent, then if I evaluate what would be the power that this thermal machine can deliver, I encounter that it has an additive component, here you have it, that you see that depends of the value of the off-diagonal elements. Should I write my total state in a basis that includes electron, tensor product, phonons? If I have non-zero contributions in here, then I have a coherent part adding to the total energy per unit time in such a way that if I look at the power delivered, is higher than if the relaxation is thermal. So this is a very prosaic, it's actually from 2015, it's a very prosaic model to account for energy transfer, but I think an indication that thinking about the dynamics from a thermodynamical point of view may actually allow you to formulate quantitative figures of merit that depend on coherence, right, in such a way that there is nothing to discuss. If there is coherence, has value A. If it's absent, is A minus something. So I hope that you think that this sort of self-contained structure makes some sense and could be a possible theoretical framework to analyze the dynamics and the spectral response of this type of molecules. It brings together actually an idea that I think is sound and probably ubiquitous, right? In the sense that really assemblies that involve molecules and a protein scaffold, what allow you is, well, to actually have a very controlled arrangement to tune electronic and vibrational degrees of freedom to create function. Does this anything to do with biology? Who knows? However, it's definitely interesting from the point of view of open systems and understanding under which conditions coherent features remain. And I think it can provide an interesting way to be able to identify what sort of principles you may extract from the functioning of natural complexes that probably devoid of some constraint that nature has and you don't when trying to fabricate a nanostructure may actually assist you for energy transfer or storage. This was a very fast, despite I'm already over time, to tell you what happened in the last, I think, 7 to 8 years. And of course, there was many people passing through the lab during that time. So in red, you have the guys that are currently working on it. This was a time where the group was quite large, so several people are already not there. Andrea Mattioni, the PhD student, is not in the picture. But these are the two guys that are being the big warriors from the very beginning. Felipe Caicedo from Colombia and Jaime Lin from South Korea. And this is Martin Plenny. So those are the ones that at this very moment are trying to compute the spectral response with the whole spectral density. And this is the new place where we are about to move. I kept this changing. Was January 2019, July but it seems it's going to be December. The building is there, the labs are there, and this will host our theory group and also a large body of experimental activities. It's called the Center for Quantum Bioscience, but this will be a quantum bio in a different, well, let's say, a different flavor, of what we've discussed today, in the sense that completely irrelevant on whether or not there may be non-trivial effects in complexes of interest in biology. Here the main aim is to be able to exploit quantum technology, in particular sensors that use nitrogen vacancies in diamond to probe biology, ranging from protein dynamics to also creation of hybrid NB molecule sensors. So the advantage is that there will also be some people, mainly chemists and also some medics, with which I think it will be quite interesting to interact. So with this I conclude. Thank you.
Thank you very much for this complete review. Are there now questions or comments?
If I understand correctly, the Renzi oscillation, is that observed in the experiment situation?
No, the experiments are more complicated.
So what's the limitation for observing that? Because if we can observe the Renzi oscillation, then we are sure that there's a maybe due to the coherence, right?
Take into account that even at the level of a Ramsey, right, that you have an oscillatory signal is not sufficient to exclude that you may have something else. So imagine that instead of preparing a coherent superposition, right, I've created a mixture that has weights that are sinusoidal. Okay? So it's a partial test.
So then what will be so-called Bell's inequality in your experiments?
That's another thing that I would argue unrelated, in the sense that here talking about entanglement, for instance, is probably not the most suitable one, in the sense that the spatial separation doesn't play any role, right? But you can think about other type of inequalities that are like Bell inequalities in time, the Leggett-Garg type inequalities that effectively test for superpositions, right? In their case, they were interested for testing for microscopic superpositions. The difficulty with this type of molecules is that it's out of the question to really perform either state or process tomography. So we are not able to access the dynamics, let's say, in the way you would do in a typical quantum information situation, where you really can reconstruct, well, for moderate number of qubits at any time, what is your raw. Here you have the spectral response, and from there you extract some aspects of the dynamics. Okay?
More questions or comments? Yes.
I'm curious, when you calculate the situation when the spectrum is structured, which master equation are you using exactly? Is there a sort of high Markovianity because of this?
No, take into account that here, what the procedure we did, well, of course, before doing the exact simulations, which are very costly, what you do is just, for instance, using a type of reaction coordinate technique, right? Where you embed in the definition of your system some of the modes that are coupled the strongest and leave as residual some Markovian path, yeah? But nevertheless, given the complexity of the spectral density, you are never sure whether you may have left outside. So that's why the analysis I show you is numerically exact. So there is no master equation. You simulate the universe.
Okay, you simulate the universe.
The universe.
Yeah. Okay. With a chain.
Correct.
The chain of
correct.
hypotheses.
Yeah.
Okay.
And in the second case, when we have the now the full spectral density just for security. We've done the DMRG analysis and a second exact simulation with a different methods, hierarchies. Okay? And at the level of the dynamics, they constand.
But still, given the spectral density, you have the path, and then the calculation is exact, numerical.
Correct.
Exact. Okay. And how much would it be difficult to describe exactly the physical system? I mean, the molecule itself, it would be...
Okay, Take into account that the molecule for me has been transformed into an electronic excitation, right? Okay, so here you see, for accounting for the spectral response, well, really what the system reacts, is well, whatever has a dipole moment will couple to the electric field of the laser. So let's say you always have to put in your description, right, as little as possible to account for the experiments, right? And the same applies to the electron-phonon interaction. This is something very, very complex, right? Because imagine in the proximity of your bacterial chlorophyll, there will be the residues of some protein that who knows what is happening in there, right? But what you're trying to see is whether you can capture that effect, right, in terms of introducing some fluctuations in the energy of your pigment, and if you need it, also in the strength of the coupling. Okay.
Last question, David.
So I don't understand this heat engine sketch.
Right, yeah, I'm not surprised.
In the plant or the chlorophyll, I mean, this is,
Right.
The hot bath, the cold bath, and some work.
Okay, exactly. So the idea is that I can think about this network really as operating in between two temperatures, right? So they are, if you think about the natural conditions, especially, then the radiation will be some thermal light coming from the sun, right? And then energy will go across this network, and then you will dissipate some energy into the surroundings. So this is what you model by means of the whole reservoir. And what we did was comparing two different theoretical models. In one case, I've really put all the phonons in the baths, right? And then this network will only couple electronically pigment with pigment. So then in the excitonic bases, right, they will couple to nothing else, and you will just have a relaxation towards the lowest energy exciton induced by the coupling to the bath. And the second would be a case where instead of having only electronic coupling, each of those is going to be strongly coupled to some mode. Okay, so now there will be a situation where really the eigenstates of your total Hamiltonian are of mixed character. Electron phonons, so vibronic system. And then we compare, in that case, what would be the power that this device can deliver. Well, the power is actually a function, has an additive component that is proportional to the off-diagonal elements of your density matrix. So it's sensitive to the fact that to some of the modes you are coupled coherently. And what does physically is that it opens up additional paths. So instead of just going thermically down the funnel, then you have the possibility to have some shortcuts due to the coherent coupling and actually end up being more efficient.
The energy flux that you calculate, is the energy flux associated with electrons, with phonons?
Not with everything, because let's say at the end of the day, you can characterize the functioning of the machine. So imagine these are your eigenstates of whatever nature they are, right? And then there is a gap to the ground state, and what you can do is put a fictitious load, so that you measure the efficiency in terms of the energy with time transfer to the load. So if you want, the first path will allow you to excite here, and then there is the issue of going down this ladder and then down to the ground state. So now you have two possibilities to do it, right? I think actually we have here. So this is sort of another cartoon of how to represent what is going on. So this is a representation of the manifold you will encounter for excitons 1, 2, 3, etc. And each of them with 0 excitations, 1 excitation, 2 excitations, etc. Right? So the point is that in one of the cases you would only have the possibility to perform thermal transitions to go down. And in the other cases, where you have the possibility, if you look at the dynamics in the separate bases, then what you have the possibility, this is like a small rotation that will allow you, instead of going here, going there, and exploit these additional paths that you only get when coherently coupled electron phonon, very much like in a James-Cummings type of interaction. Okay? So this was mainly to illustrate that if you want to argue that coherence is relevant for function, then you then have to formulate, to identify some task, or to provide some way to measure the efficiency of your aggregate in such a way that when coherence is present, it does better. Yeah?
Okay, I think we need to finish here. Susana, she said she will be here until Friday morning, so if anyone wants to talk to her, just let me know. I will accommodate the agenda. Then let's thanks again, Susana. Gracias.